The approach to safety in the chemical industry was originally driven by insurance needs. The term usually used in the industry, loss prevention, reflects these origins. In chemical and petrochemicals, the three major hazards are fire, explosion, and toxic release. Of these three, fire is the most common. Explosions are less common but cause greater losses. And toxic release is relatively rare but has been the cause of the largest losses. Because loss of containment is a precursor for all of these hazards. Much of the emphasis in loss prevention is like the nuclear industry, which is usually considered part of the process industry, on avoiding the escape of explosive or toxic materials through leaks, ruptures, explosion, and so on. The three major hazards related to the chemical industry have remained virtually unchanged in their nature for decades. Design and operating procedures to eliminate or control these hazards have evolved and been incorporated into codes and standards produced by the chemical industry, professional societies, and others. This approach sufficed before World War II because the industry operated on a relatively small scale and development was slow enough to learn by experience. After World War II, however, the chemical and petrochemical industries began to grow in complexity, size, and new technology at a tremendous rate. The potential for major hazards grew at a corresponding rate. The operation of chemical plants also has increased in difficulty, and startup and shutdown have especially become complex and dangerous. The effect of the changes has been to increase the consequences of accidents, to increase environmental concerns such as pollution and noise, to make the control of hazards more difficult, and to reduce the opportunity to learn by trial and error. At the same time, the social context has been changing. In the past, safety efforts in the processing industries were primarily voluntary and based on self-interest and economic considerations. However, pollution has become of increasing concern to the public and to the government. Major accidents, such as the Deepwater Horizon oil spill, have drawn enormous publicity and generated political pressure for legislation to prevent similar accidents in the future. Most of this legislation requires a qualitative hazard analysis, including one, identification of the most serious hazards and their contributing factors, and two, modeling of the most significant accident potentials. These factors led industry to increase its proactive efforts to analyze potential hazards more carefully and to reduce emissions and noise. The accidental release of MIC, methyl isocyanate, at Bhopal, however, demonstrated that technical hazard analysis by itself is not enough and that management practices may be even more important. Applying hazard analysis in the chemical industry has special complications compared to other industries, which makes the modeling of causal sequences especially difficult. Although the industry does use some standard reliability and hazard analysis techniques, the unique aspect of the industry have led to the development of industry-specific techniques. For example, the hazardous features of many chemicals are well understood and have been cataloged in indexes that are used in the design and operations of plants. A hazard analysis technique developed for and used primarily in the chemical and petrochemical industries is called HAZOP, Hazard and Operability Analysis. This technique is a systematic approach to examining each item in a plant to determine the causes and consequences of deviations from normal plant operating conditions. The information about hazards obtained in this study is used to make changes in design operating, and maintenance procedures. Has updates from the mid-1960s. Newer hazard analysis techniques can be performed earlier before the design is complete, and the results are used to build simpler, cheaper, and safer plants by avoiding the use of hazardous materials, using fewer of them, or using them at lower temperatures or pressures. Accident investigation is of course done if losses occur, but proactive analysis and design efforts are much more heavily emphasized.